Grab your cheese curds, math nerds. We're going to talk about sequences. We're going to start with what I call some basic results, not because they're easy, but because they form a basis of a lot of stuff we're going to do later. Suppose that the ANs have limit capital A and the BNs have limit capital B. So not only do the sequences converge, but we've given names to the limits, A and B respectively. First up, if A prime is a number that isn't the limit of the A's, at most finitely many of the ANs are equal to A prime. Observe I'm actually not saying anything about how many terms of the sequences are or are not equal to A, just if A prime is one specific number that isn't the limit of the A's, at most finitely many terms are equal to that. Second, if I take a limit of a new sequence formed by AN plus BN, that sequence has limit capital A plus capital B, which is the limit of the A's plus the limit of the B's. Third, I get a similar thing with products. The limit of the sequence AN times BN has limit A times B, the limit of the ANs times the limit of the BNs. There's a similar result regarding reciprocals. Yeah, basically limits distribute across sums, products, and reciprocals as long as all the limits exist. All of these results started with the assumption that the sequences AN and BN had limits. If the sequences AN and BN don't have limits, none of this really applies. Also in that last one, observe, if the limit of the B's is not 0, then you can do this trick. Okay. Now definitely if the limit of the BNs is equal to 0, you don't want to end up with 1 over B. That would be 1 over 0. That would be bad. Also, so look back at problem 1. If the limit of the BNs is capital B, which is not 0, then how many terms of the sequence can actually equal 0? That's asking how many terms of a sequence can equal one specific number that isn't the limit of that sequence. And part 1 says at most finitely many, which means if capital B is not 0, at most finitely many of the BNs are equal to 0. And if only finitely many BNs are equal to 0, there's a last one equal to 0. So you could ignore up to that point and be left with all the terms after that point, and then you can take a limit from that point forward. Now what we're going to prove right now is this product law. If the limit of the ANs is capital A and the limit of the BNs is capital B, then the limit of the product AN-BN is capital A times capital B. There's really two important cases to split this into. Suppose one of the sequences, for the sake of argument, the BNs, has limit 0, and suppose it doesn't. Well, if the limit of the BNs is 0, then capital B is 0. So on the right-hand side there, I just want to prove that the limit of AN-BN is A times B, but if B is 0, I just want this to equal 0 here. So I just want to prove the limit of AN-BN equals 0, under the assumption that capital B is 0. So now, I don't actually know if capital B is positive or negative. What I do know is it's not 0. So let's just assume it's positive so I can draw this picture, and I'll just stick capital B up here. So if epsilon is positive, okay, then so is epsilon over the absolute value of A plus epsilon. Absolute value of A is at least 0. Add epsilon to it, still positive. Epsilon over a positive number, still positive. So what this means is that since the BNs have to be getting really, really close to B, they cannot be really, really close to 0. So if epsilon over the absolute value of A plus epsilon is a very small positive number, since the terms of the BN are being trapped close to capital B, they are not especially close to 0. So past a certain point, the BNs are at least as big as this small positive number here, because they have to be trapped close to capital B. But also the ANs have to be getting close to A. Now capital A can be 0, it can be non-zero, it doesn't really matter. But whatever epsilon is, eventually I'm trapped very, very close to capital A, which means past a certain point, the ANs are within epsilon distance of capital A. So I can pick a really large index that's bigger than both of these, which means, first of all, the absolute value of AN-BN minus 0, well, that's just the absolute value of AN times the absolute value of BN. But the absolute value of AN was less than the absolute value of A plus epsilon, and the absolute value of BN was less than this quotient. because I assumed I went far enough out in the sequence so both of these things were true. Now the capital A's plus epsilon cancel out, and that means the distance from an, bn to 0 is less than epsilon. So what did we find? For any epsilon which is positive, I was able to pick n's past a certain point so that the distance of an, bn to 0 was less than epsilon. This is exactly the definition of the limit of an, bn is 0. That was true if capital B was 0. What if capital B isn't 0? Well, again, I need to prove something about an arbitrary epsilon which is positive, so let epsilon be positive. Then past a certain point, the ANs are less than capital A plus epsilon. This is very similar to the last time. But now that B is not 0, I can actually divide by its absolute value. The epsilon over the absolute value of B is still positive, which means I can also say not only is an, close to capital A, it's also within epsilon over 2b of capital A. And since epsilon over 2 times the quantity absolute value of A plus epsilon is still positive, I can guarantee that the BNs are that close to B. So the ANs are pretty close to A. They're less than epsilon distance to A. They're also less than epsilon over 2b distance to A. And the B's are less than epsilon over 2 times the absolute value of A plus epsilon distance to B. Basically what we're doing is we're saying the ANs can be made very, very close to A. And the BNs can be made very, very close to B. How close? As close as we want, and we're picking these specific distances. The ANs need to be epsilon close to A. They also need to be epsilon over 2 capital B close to A. And the BNs need to be epsilon over 2 times the absolute value of A plus epsilon close to B. Why are we picking these random-ish numbers? Well, if I look at the absolute value of an, bn minus ab, the goal is to get that this is somehow less than epsilon. If I can guarantee that an, bn minus ab is less than epsilon, then an, bn is really close to ab, and that's the goal. But all we're going to do is employ this stupid little arithmetic trick by subtracting and adding the same quantity, an times capital B. Then we're going to use the triangle inequality. Okay, so I split this up into 2 absolute values. From this first one, I factor out an, and from this one, I factor out capital B. Of course, I'm factoring them out with an absolute value. Now, what did we assume? First of all, an is less than the absolute value of A plus epsilon, but also an minus A is less than epsilon over 2 times B, and also bn minus b is less than this monstrous quantity. So we assumed n was large enough to get all 3 of those things, and now a bunch of stuff cancels. We get an epsilon over 2 plus an epsilon over 2, which is just epsilon. So that was a sort of tricky one, the product law. But work through the following. They're generally a little simpler than that last one, but remember the goal is to derive certain statements about limits. Okay, remember, these sample problems are either designed to test something you just did or to lay groundwork for stuff we're going to need later. So it's important that you really are pausing and trying to work through these problems, not just skipping forward 10 seconds. So hopefully we actually tried all of these things. Okay, moving forward. Yeah, if you have done all of these problems, you'll see the limit of 2 things is equal to the sum of the 2 limits. Also, scalars factor out of limits. And between these 2 facts right here, what you end up with is you're saying that taking limits is a linear operator of sorts. So if you have a space of sequences, you can think of sequences as vectors. You can multiply them by numbers and you can add them together and get new sequences. And limits are a way of taking sequences and getting out real numbers, and this operator of taking limits is a linear operator, which means all sorts of stuff you may have learned in linear algebra can actually be applied to the study of limits. Let's work through an example, show that this sequence has the following limit. You could do it with your epsilon capital N definition, but that's a really convoluted way to get the answer now that we have some basic groundwork. Well, L'Hopital's rule isn't part of that basic groundwork. First of all, we haven't proven it. Second of all, L'Hopital's rule requires the use of derivatives, which is not a word we've even come close to defining. Here's how we're going to do it. We have established that the limit of 1 over n is 0, which means -1, well, that's just 3 times 0 plus 1, duh, but 0 is the limit of 1 over n. Now, since I know that that limit exists, I know that scalar multiples, specifically multiplying by 3, can be factored in and out. So I can factor the 3 into that first limit, and we also know that constant sequences have that same limit. So the constant 1 can be reinterpreted as the limit of the sequence, which is just 1 over and over again. But now what do we have? We have the limit of one sequence minus the limit of another, and we already know that this sequence has limit 0, and we already know that this sequence has limit 1. So since we know both of these sequences have limits, we can, in a sense, factor out this limit operator and just end up with this limit right here, the limit of 3 over n minus 1. Very similarly, you can conclude that the limit of 2 over n plus 5 is just 5. It's really the same steps. Since that limit is non-zero, I can conclude that this limit down in the denominator is not 0, so this limit divided by that one can be reinterpreted as this quotient, which algebraically simplifies down to this. And we've just established that that limit on top is -1 and that limit on bottom is 5. So overall, the limit of 3 minus n over 2 plus 5n is -1 over 5. I want to stress that the order we did these steps was pretty deliberate. We never took any operations of limits, like factoring out a constant or factoring a limit across a sum or distributing it across a sum. We never did it until we had already established that all the underlying limits existed. I didn't just go right into saying this. I didn't say the limit of 3 over n minus 1 is 3 times the limit of 1 over n minus the limit of 1. Because in order to distribute the limit across that difference and factor out the constant, you need to know that the limits already exist. And until you get to this stage here, you don't actually know that the individual limits exist. But if you start here, since you know those limits exist, then you can factor the limit out and go that way quite directly. It seems like a silly distinction, but it's really a matter of only doing steps once you know they are justified. Another sample problem. Suppose p of x is a polynomial of degree n with leading coefficient p. Remember, the leading coefficient is the real number multiplying the highest power of the variable, and the variable in this case is denoted as x. And q of x is a polynomial of degree m with leading coefficient q. Then if I take the limit of p of n over q of n, if the degree of the numerator is smaller than the degree of the denominator, the limit is 0. If the two degrees are equal, the limit is the ratio of the leading coefficients. And if the degree of the numerator is larger than the degree of the denominator, the limit is the sign of the ratio of leading coefficients times infinity, where the sign of a number is 1 if the number is positive and -1 if the number is negative. It's 0 if the number is 0, but that's actually guaranteed not to happen here because leading coefficients are never 0. So go ahead and try to work through this. It's a little trickier than the one we did because the polynomials are arbitrary, but very similar results will help. Now, if you did manage to work through this, what you've basically done is justified something that is typically introduced in pre-calculus about end behavior of rational functions. And now we really have a firm justification for it, at least when we're only talking about sequences and not the functions that have arbitrary real inputs. We'll see later it's pretty much the same thing, though. Here's a familiar result called the squeeze law. Suppose I have 3 sequences, an, bn, and cn, that happen to obey these inequalities. The an's are never bigger than the bn's, and the bn's are never larger than the cn's. Also, the an's and the cn's have a limit, and they're the same limit, and we're calling it capital L. If all of this is a given, then the bn's have to have the same limit. So the proof is actually fairly straightforward. So Let epsilon be positive, it doesn't matter what it is. Since ANs and CNs have the same limit, there's one index past which AN is epsilon close to L, and there's another index N2 past which CNs are epsilon close to L. So again, if I go out past the maximum, I can get both of them. If the ANs are epsilon close to L, they're at least as large as L minus epsilon. This inequality, less than or equal to should be there, was part of our given. And this inequality is true because the CNs are epsilon close to L. Overall, you end up that the BNs are trapped between L minus epsilon and L plus epsilon, which is to say the distance to L is less than epsilon. So for any epsilon, past a certain point, all of the BNs are epsilon close to L. That's exactly what we were trying to prove. Now here is something we introduced a little bit ago. The Heine-Borel Theorem says a set is compact. Now remember, a compact set is a pretty abstract definition. It says every open cover of the set has a finite subcover. This is true in the real numbers if and only if it is closed and bounded. Now the proof comes in 4 steps. We're trying to show a set is compact if and only if it's closed and bounded. Step 1, if it's compact, it's bounded. Step 2, if it's compact, it's closed. Between the two of those, if it's compact, it's closed and bounded. Then look at this last step. If it's closed and bounded, it's compact. That will close the proof altogether in a nice compact way. But a nice prerequisite for that 4th step is this 3rd one. If it's closed and a subset of a compact set, then it must be compact, the set A. So these are the 4 things we have to do. And yeah, we did the first one on a previous video. If it's compact, then it's bounded. In a sense, we're a quarter done. In a much more real sense, we aren't, because that was by far the easiest quarter to do. So we have shown that a compact set must be bounded. Let's show a compact set must be closed. We're going to prove the contrapositive. If a set is not closed, then it's not compact. So assume the set A is not closed. That doesn't mean the set is open. Right, a set doesn't have to be open or closed. If it's not closed, however, it is missing a limit point. Yeah, there must be a limit point of the set A that isn't in A. That's what it means to not be closed. So let's let X be this point, which is a limit point of A, but is not in A. So define the sets AN to be these unions of intervals from minus infinity to x minus 1 over n, and then from x plus 1 over n to infinity. Notice these are open sets. They're a union of 2 open intervals, and any union of open sets is open. So each of these ANs is open. Here's basically what we are doing. Okay, we have assumed that there is, in the real number line, a point x where x is in A, sorry, not in A, and it's a limit point of A. So what we're doing is we're defining a bunch of open sets. Everything up to x minus 1 over n, and then everything past x plus 1 over n. The union of these two things is exactly the set A sub n. Now what happens as n gets larger and larger? 1 over n gets smaller, which means this cutoff point is marching this way, while this cutoff point is marching that way. In other words, the union of all of those sets is everything except for x. Since x is not in A, and their union is everything except for x, the union of these open intervals must in fact cover A, because the only point they miss is x, and x isn't in A. So this infinite union of sets now covers A, and they're all open. So what we have is an open cover of A. So should we prove the fact that the union of these sets is in fact R minus X? Well, the picture on the previous drawing kind of did most of the work. I mean, here's how we can really go through it in detail. Okay, so AN is negative infinity to x minus 1 over n union x plus 1 over n to infinity. So we need to show that the union of A sub n is everything except for x. So to prove it, we'd have to say let y be anything in the set of all real numbers minus x. In other words, y is a real number that isn't equal to x. Let's just assume for the sake of argument y is bigger than x. In other words, y minus x is positive. Now since 1 over n has limit 0, this implies there exists a capital N so that 1 over n is less than epsilon, where epsilon is equal to y minus x. So 1 over n is less than y minus x. Up on this number line up here, I've got x, and we've got y, which is bigger than it. Whatever this distance is, I'm calling this epsilon. It's y minus x, and there is a 1 over n that's smaller than that, which means that if I were to draw the set a sub capital N, it would go from x plus 1 over n onward to infinity and would include y. So y belongs to the set a sub n, and therefore y belongs to the union of all of the a sub n's. So any y that isn't x exactly belongs to one of these. In other words, they form an open cover of everything except for x. And again, since x was not in the set A, if I cover everything except for x and x isn't in A, then I've covered A. So since A was assumed to be compact, okay, I have an open cover of A, which means I have a finite subcover, but these are nested. So if I have a finite subcover and they're nested, they're an increasing sequence of sets, any finite union of them is in fact just equal to the one corresponding to the largest n. Since the intervals were just squeezing down on the point x, if I can stop this process at any particular index, all I've done is stopped moving towards x, which is just that one set a sub n. So since the A can be covered by a finite collection, A must be a subset of one particular AN. What this really is A sub capital N, but it's also the union as n goes from 1 to capital N of A sub little n. Because they're nested, as I union them all together, if I keep unioning these together, what I've really done is just stopped at one particular index. Which means, since A is a subset of this union, the intersection with the complement, which is just from x minus 1 over n to x plus 1 over n, must be empty. But that means x is not a limit point, because now I have a little epsilon neighborhood of x, specifically x minus 1 over n to x plus 1 over n, which does not intersect the set A. And if I can do that, I'm not a limit point. So if the set A is compact, it cannot miss any of its limit points, which suffices to prove that if a set is compact, it must be closed. It must contain all of its limit points. Moving on, let's suppose A is closed and a subset of B, and B is compact. We claim A must be compact as well. So bear in mind, we've already proven a compact set is bounded. We did that in a previous section. We just finished the proof that a compact set is closed. So we now know compact sets must be closed and bounded. Now what we're doing is we're working towards the converse. If a set is closed and bounded, then it's compact. But this is going to be a useful stepping stone. If a set is closed and a subset of a compact set, then the set A must also be compact. So since the set A is closed, by definition, that means its complement is open. Remember, that's the definition of being closed we're working with. So suppose you have an open cover of A. In other words, I have a collection of open sets, not necessarily finite or countably many. I'm just calling them U sub alpha. There's a weird collection of open sets, but they do cover A. What I'm going to do to this open collection of open sets is I'm going to add one more open set to it, the complement of A. So all the U alphas are open, the complement of A is open, so altogether I still have a whole bunch of open sets. So suppose this is our set A. My U sub alphas are open sets that happen to cover A. And there's a weird collection of them. I don't even know how many of them there are. I'm just trying to draw them as quickly as possible. Here are all of my U sub alphas. A bunch of open sets that happen to cover all of A. What I then do is I add one more open set, which is just everything outside of A. Again, I'm drawing two-dimensional pictures, but the idea is I started with a bunch of open sets that cover A, and I add one more open set, the complement of A. Well, what have I covered now? So since the original set's U alpha covered A, and I added the complement of A, what I've done now is covered everything. Since I've covered everything, I've certainly covered B. Now, the set B was assumed to be compact. So I can find a finite collection of those sets that in fact cover B. Since A is a subset of B, if I've covered B, I've covered A. But we do have a problem. I wanted to show that any open cover of A has a finite subcover of A. But we did this weird intermediate step where instead of looking at the original open cover of A, I threw in one extra open set, R minus A. So I found a finite subcover from that collection, which might include R minus A, in which case it wasn't a subcover of the original collection. It was a subcover of our modified collection. So we might not have a subcover drawn from the original U alphas, because we did in fact change our collection by adding one extra open set. We will resolve this issue, don't worry. So A is closed. B is compact and B contains the set A. We started with an arbitrary open cover of A, added the complement of A, another open set. We passed to a finite subcover of that, which now covers B. There are two possibilities. The finite cover we passed on to includes the complement of A or doesn't. Well, if it doesn't include the complement of A, then we have a subcover of the original collection, which covers B and therefore A. And that is done. I mean, we're done. If we find a subcover of the U alphas that covers A, that's all we wanted to do. So if our subcover, which covers B, didn't include the complement of A, then we found a subcover of A from our original collection U alpha, and therefore we're fine. So let's assume that the finite subcover of B we moved to actually does contain the complement of A. So I have a finite collection of sets. I'm going to call them U1 through UN, but also including the complement of A. That's still finitely many. I have n plus 1 sets here. This is a cover of B. If I just remove that set right there, I don't necessarily cover B. But I don't care if I covered B or not. The goal was to find a finite subcover of A. So this covers B. If I take this out, I'm only removing points that weren't in A to begin with. So since the U's, the finite collection of them, with the complement of A covered B, if I remove the complement of A, I am not affecting what I have covered in A, because I only took away the complement of A. So since this covers A, if I remove the complement of A, I still cover A, because the only set I removed was exactly a set that didn't cover anything from A. So for any element of A, since A is a subset of B, that X must also be an element of B. Therefore, it's either in one of the UIs or in the complement of A, because this collection covered B. But since X is in A, I'm certainly not in the complement of A, and therefore I'm in one of the UIs. Which is to say, from our finite subcover of B, just throw out the complement of A, and now you have a finite subcover of B. Of A, I'm sorry. So now we have a finite subcover of A, which was the goal. From any open cover of A, we were able to find a finite subcover of A, which is to say A is compact. Okay, here's what we've shown so far. If a set is compact, it's bounded. If a set is compact, it is closed. Great, if a set is compact, it's closed and bounded. We want to show if a set is closed and bounded, then it's compact. Now, since A is bounded, I can contain it in an interval. It has an upper bound, which I'll call B, and a lower bound, which I'll call A. So everything in A is less than or equal to B and bigger than or equal to A, and therefore it's in this interval. Any bounded set can be contained in one of these closed intervals. Notice A is now bounded. It's contained in a closed set. If I can show that this interval is compact, what we'll have is a closed set in a compact set, and therefore, by the previous page, A will be compact. So any bounded set belongs to one of these intervals here. If intervals that look like that must be compact, then any closed set, which is bounded, must also be compact based on the previous slide. So now what we have to do is we have to show the interval from A to B, including both endpoints, is compact. Let's suppose to the contrary it isn't. There is an open cover that does not have a finite subcover. So we assumed that the interval from A to B has an open cover with no finite subcover. Notice I'm not saying that every open cover has no finite subcover, just that there is one particular open cover with no finite subcover. So imagine splitting this interval in half. Instead of going from A to B, put it in two pieces, from A to the midpoint and then from the midpoint to B. Certainly, the interval can be expressed as the union of these two pieces. Now, since the entire interval cannot be covered with finitely many of the sets U, at least one half of it can't be covered with finitely many of the sets, maybe both of them, but certainly I cannot take finitely many and cover the left half and then finitely many and cover the right. If I could do that, I could cover the whole thing with finitely many. So at least one half cannot be covered with finitely many U sub alphas. Whichever half that is, call it I sub 1. So here's what we're doing right now. Okay, so we've got our set from A to B. Then what we have is our U sub alphas are a whole bunch of open sets. I'm just drawing open intervals, but they can be any open sets you want. These are all of my U sub alphas, and I'm trying to draw it crazy-like because I want it to look like there's infinitely many of them. If I split this into two distinct subintervals, from A to the midpoint, A plus B over 2, and then A plus B over 2 to B, maybe it's possible to find finitely many of the U sub alphas that covers the left. But I then could not possibly find finitely many U sub alphas that covers the right, because if I could, then what I could do is I could take this union and I'd have finitely many open sets that covered the whole thing, and I assumed explicitly this had no finite subcover. So if one half can be covered with finitely many, then the other half certainly can't be. In other words, at least one half cannot be covered with finitely many of the U alphas. So from our original interval that didn't have a finite subcover, at least one half doesn't have a finite subcover. Which means we took our assumption that we had an interval with no finite subcover and concluded that half of it has this same property. So yes, it's the same problem on a smaller interval. So do it again. I'm going to cut whatever bad half I took before and cut it in half. One of those halves will not have a finite subcover. Call it I2. Cut that in half, and one of those halves will not have a finite subcover. Call it I3. Cut that in half, and so forth. I can always cut it in half and find one of the two halves, maybe both, but at least one, that doesn't have a finite subcover from our original collection U alpha. So from the original interval from A to B, this was our interval that had an open cover with no finite subcover. Maybe this half has no finite subcover, and then 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 this half, and then this half, etc., etc. I can keep going. What's going to happen as I keep doing this process over and over? What we end up with are nested intervals, whichever half cannot be covered with finitely many elements of our original cover, which are nested. The left endpoints are only increasing and the right endpoints are only decreasing. And in a sense, we haven't done anything except create an infinite sequence of intervals that have no finite subcover, and the intervals are getting smaller. Instead of one interval that can't be covered, yeah, we got infinitely many. So instead of one problem, we got way more than 99. But it turns out in this case, having lots of problems is better than having one. Here's what we have so far. We had our interval from A to B, which had this property that there was an open cover that had no finite subcover. So here it is. Here is our interval from A to B. We kept splitting it in half to get halves that had this same property, where our endpoints AN are always increasing and our right endpoints BN are always decreasing. But they're also bounding each other. The ANs can't ever surpass the BNs. So the ANs and the BNs are both bounded and monotone. Bounded and monotone in different directions, but still both bounded and monotone. And what do we know about bounded monotone sequences? They have real limits. So I'm going to call the limit of the left endpoints alpha and the limit of the right endpoints beta. But what else do we know? They're the endpoints of intervals that are shrinking by a factor of a half. So the length of that interval is 2 to the minus n, or 1/2 to the n, times the length of the original. This length here goes to 0. This is a fixed constant, which means the limit of the length of the individual intervals must be 0. So if the alpha ends are increasing towards alpha and the beta ends are decreasing towards beta and the distance between them is going to 0, well then, alpha must equal beta. So whatever this shared limit is, I'm going to call it C. It must be in the original interval, and also the AN BNs were chosen so that those intervals never had a finite subcover. But remember that we have an open cover of the interval from A to B, and C is in that interval, so it must belong to one of these open sets. But what do open sets have? They have wiggle room. So there's got to be an open interval C minus epsilon to C plus epsilon in one particular element of our open cover that we're just calling U. Okay, so from our AN, BN, our ANs were increasing this way, and our BNs were decreasing this way. We have a fixed limit C of both the ANs and the BNs. But C must belong to one of the elements of our open cover, which means there's a C minus epsilon to C plus epsilon that is a subset of this same open set, because U is an open set, which means if C is in it, I can wiggle around just a tiny bit, both left and right. But what do I know about the ANs? They're converging to C. And what do I know about the BNs? They're also converging to C, which means eventually some AN and some BN are both going to be in this interval, which means they're going to be covered by one particular open set, and that's a contradiction. Delaney sees it. So for sufficiently large n, the ANs are very close to C because they're converging to C and they're doing so from below. Remember, the ANs are increasing. So the ANs are at least as large as C minus epsilon. But also the BNs are no larger than C plus epsilon. In which case the interval from AN to BN is contained within the interval C minus epsilon to C plus epsilon, which was contained within the open set U, and therefore that interval did have a finite subcover, just one single open set U. So any open cover of the original interval must have a finite subcover. If I assumed it didn't, we got a contradiction through this limit point C. Therefore, any open cover of a closed bounded set has a finite subcover because any open cover of one of these intervals has a finite subcover, and any closed bounded set is a subset of one of these intervals, and we've proven that any closed subset of a compact set must be compact. So any closed bounded set must be compact. And that's the end of the Heine-Borel theorem. At least when we're talking about subsets of the real numbers, being closed and bounded is exactly equivalent to every open cover having a finite subcover. Whew. So why do we bother? If they're the same definition, why do we have both of them? Well, being closed and bounded is a pretty straightforward thing to talk about. Closed means has all its limit points, or even more succinctly, complement is open. And being bounded is a very intuitive notion. And what we've shown is that from this, you can get this property about open covers having finite subcovers. So why bother talking about finite subcovers and all that nonsense In certain contexts, that definition can be very helpful, and that definition can actually simplify proofs. And what we've shown is it doesn't matter which one you use. So sometimes it'll be a lot easier to say, oh, the set is closed and bounded. But in other proofs later on, it'll be easier to say, every open cover has a finite subcover. And now we know going back and forth between those two things is totally free. We can do one, we can do the other, we can go back and forth, as long as we are talking about subsets of the real numbers. In other sort of spaces, they're called, or other like master sets that you work in, these two definitions might not be equivalent. Sometimes they are. There are lots of sets, lots of spaces where closed and bounded is equivalent to compact, but there are some where it isn't. But for the real numbers, which is the focus of our course, yes, closed and bounded is the same thing as compact. Yeah, so if we're in the real numbers, closed and bounded is the same as compact. What about things that don't take place in the real numbers? Well, mathematically, it's perfectly valid to talk about them. But then you can start arguing, does it make sense? And I mean, a sort of stock reply is like, oh, complex numbers have lots of applications. Okay, but complex numbers are not nearly very far along the weird scale of topological spaces. What's the point of talking about very exotic types of constructions where closed and bounded isn't the same as compact or other sort of weird things happen? It can just be a mathematical curiosity, and honestly, that's good enough. I mean, why not? Thank you, Delaney. Well, hopefully that extended proof of the Heine-Borel theorem wasn't too onerous. But now that we've gotten some familiarity working with sequences, we're going to keep charging through and learning about properties of sequences. So come on back to the next video.